There we go. So we've started recording. So I just want to introduce briefly who our speaker is today. A lot of you have already seen the advertisements for today's presentation, and you got to see our speaker, Tom, and talk to him a bit earlier in this evening's startup. We were very lucky in John Abbott College that the RASC Montreal Center picked up one of these Star Analyzer 100 filters and let our students use it a couple of years ago. And two of the students who were part of the group, Julian and Danielle, are on with us tonight. And at the end, they might have a few questions and things that they still had outstanding and questions to from their project. But what was amazing for us is they're using this piece of software to capture spectra of stars and analyze them. And anytime they weren't sure what to do, they went to the website and there were videos to help them. There was a forum where they could ask questions, and Tom was emailing back and forth with them in real time while they were working through their project. And so I got to know Tom a little bit by email at that time, and then again this past term when one of my students, Nick, was working with him on the same Spectra project. And so it seemed natural to me to end my foray into astrophotography this year for John Abbott College by asking Tom to come and give us a talk. So Tom has been a contributing editor to Sky and Telescope for the last 7 years. His product, the Star Analyzer, was actually one of the hot products in 2011, shortly before he started working with Sky and Telescope. And he has given talks around North America. And it was actually at one of his talks at NEAF that David and our group from Montreal Center got to meet him and decided to invest in the Star Analyzer. So without any further ado, I'm going to turn this over to Tom because he will give us a fantastic intro to how to really engage the night sky from a more scientific perspective, but an attainable approach to spectroscopy. So Tom, we're all yours.
Looking at, I like that Nicholas and Paul are sort of color coordinated with the greens there tonight. That's a nice touch. I know you guys planned that. So let me share my screen. We'll get things started here. There's what I'm seeing. There we go. So thank you so much for the gracious introduction and for the opportunity to talk tonight. I'm really excited about spectroscopy, as you're going to hear. And the reason I'm excited is because I can share it with you, and some of you will go away from this and maybe even pick it up and do some on your own. And my goal is that some of you do that, not so I sell stuff. This is just a hobby business for me now, but because the exciting thing for me is to see people learning something new, especially something that's so key to the stars and to what we study and look at through our telescopes. So I'm going to talk for about 40 minutes, and then we'll take Q&A, and I'm always available. I love the topic, so let's get started. For those of you who are observant, you'll notice that this rainbow is flipped, and we need to talk to our graphic artists about that. I bought this about 10 years ago on the web. But so how is it that we've learned so much about the universe, but we've barely set foot outside our own front door? You know, we can see images of the universe that are in 2 dimensions, and we learn things from that. We can get fleeting glimpses of a 3rd dimension during eclipses. And if we watch for a while, we can see a 4th dimension. I'm going to go back and forth between 2 slides. I think you can probably see a handful of stars, especially up here in this corner, going on and off. And those, again, are a time dimension. But if we spread the colors out, and by the way, this is an image from Lake George, not all that far from you, especially compared to me being out here in Seattle. And by the way, I know there's somebody here I saw from Victoria, just up the street a little bit. If we spread the light out, we get an as-if 5th dimension. And it reveals barcodes, as if, that help us learn something about what we're looking at. Now, I'm going to spend a little time talking about the science and then a little bit about equipment, but the primary thing I want to show you is some of the cool stuff that we can do. So bear with me on that. You can see we can actually identify the composition of whatever it is we're looking at. So why is it you might want to do this? Well, you might be interested in capturing star spectra if you remember the thrill of that first image you took of the moon. Oh, and by the way, I noticed, just to interrupt myself for a second, Jane is here. Jane's a user of the software and the star analyzer also. So remember that thrill, that first moon image you took? It was blurry, it was overexposed, but for you, it was like the Mona Lisa. You were showing it to everybody you could find. It was gorgeous. And when you take on something new, like spectroscopy, you get to recapture that thrill of excitement and discovery. Maybe you want to do some new science, recreate some of the historical discoveries, and even contribute to some of the pro-am projects that are going on. Maybe you want to do a new activity, but you don't want to spend a lot of money on a big initial investment, because a lot of things that we might want to do, of course, require really high-end equipment. And you'll see that's not the case tonight. And this, I think, is the most telling of the reasons you might want to do spectroscopy. When you own the data, and the students are here like Julian and the others who have used our product to capture spectra can confirm this. When you own the data, it becomes much more interesting. You end up reading about it and things stick. I know for me, things go in one ear and out the other at this age. But when it's your data, things tend to stick a little bit more, partly because I think you have a conceptual framework onto which to hang what you're reading. Maybe you're tired of driving to a dark sky site that may currently, of course, be closed. And one of the nice things about spectroscopy is it's much less impacted by light pollution. And, you know, for me, I was an imager, but imaging really never captured my attention. The subtle differences that you can do with different processing really went right over my head. Frequently, I couldn't even spot the difference in a before and after picture, which had been processed in some way. But dark skies aren't necessary to do some interesting stuff. And the other thing is you don't have to have a PhD to do what we're talking about. I think a lot of people go, oh, you know, that's really over my head. I don't want to do the reading that I've got to do. I'd love to learn a little more. And you don't have to be an expert. If I can do it, you can do it too. You know, the thing I love about being in software is Control Z, edit, undo. I am all thumbs and break just about every piece of telescope equipment I use. But so I'm not really a hardware guy. And you don't need to be a really high-end person or set out for, you know, 20 hours worth of integration time to get interesting images. And if you're like me, you're not a person who builds things or want to do a lot of calculations and sort of figure out what goes together. And as you'll see as we go on, things are pretty straightforward. And if you're doing outreach, and I understand, in fact, I wanted to compliment the group there in Montreal, because I know you do a fair amount of outreach, even a little bit of spectroscopy. To me, that's one of the most important things that we can be doing these days. And a colorful image on a live screen really captures people's attention. And, oh, I missed that. The second part of that number 2 is you want to mentor some of the next generation young astronomers. And finally, you want to hang out with a cool crowd. The cool crowd doesn't include me. I'm a wannabe. But it does include a lot of really interesting people doing interesting things. And because it's a relatively small group, they love helping other people to learn. So especially, I know I'm looking at the images here on the video of the other guests here tonight. I know not all of us are as young as we used to be. And it may be that you're thinking, I just don't have it in me to climb another learning curve. But I think you'll find that there's so many people who love to help. And of course, the web makes life easier. Okay, that's a lot of words. This is a new slide to me. I wanted to put this in here because I'm going to be showing you things that confirm this as we go along. Okay, let's take off. Tiny bit of history here. There's Sir Isaac Newton on the right. Again, whether it's using a prism like over here, or whether it's using a reflecting surface like a DVD. Sir Isaac Newton, again, quite some time ago, was one of the people who helped us. In fact, we're standing on his shoulders amongst others. Fraunhofer invented spectroscopy. He developed the instrument. Look at the clothing these gentlemen are wearing here. They didn't know what they were looking at, but they knew it was interesting, and he observed the spectra of stars and could tell that things were different on different types of stars. But let's go back in time considerably further. Let's go back 500 million years. This is a fossil from that era. Now, Professor Parker looked at that and he said, you know, that sort of looks like the fine lines that we would see on a grating or on a reflecting DVD. And he hypothesized that maybe this huge explosion in diversity that occurred back then in the Cambrian age was the result of the differentiation that was now evolutionary significant visually. Who knows? But let's move on. So now Bunsen, you know, Bunsen invented the Bunsen burner to burn things. He ran the light through a prism and he looked at the results. One interesting thing about Bunsen is he deliberately didn't patent the Bunsen burner. He, this was a different era, was saying, this is for the good of humanity. I'm going to make this available to anybody who wants to use it for scientific discovery. That's really remarkable and as I said, somewhat rare. We're not going to spend a lot of time talking about Kirchhoff. Some of the current students here probably could talk better about him than I can, and frankly, a lot of you in the audience can probably talk about some of the astronomical things we're going to look at in a few moments. So just briefly, Kirchhoff, because I want you to appreciate that we're going to see two types of spectra. This is, you can see it's a rainbow, but it's got some gaps. And the other kind of spectra is essentially a dark field with some lines. Which you get depends on the temperature and some other things involved in how the light got to you. But I just wanted you to appreciate that there are two different types of spectra. But notice, incidentally, that the lines between these lines line up. So whether it's an emission or absorption spectrum, the same data is available. And these are chemical fingerprints. Now, those of you for whom you're going, oh my God, I've taught this for years, or I've read this for years, or let's get on with it. Give me another minute or two and we'll be on to more interesting things for you. These are like chemical fingerprints that let us study the stars, as we'll be seeing. This is the periodic table of spectra that, that we developed here. It's actually available as a poster. You can see hydrogen there. There's the hydrogen bomber lines. You can see that hydrogen has a very different spectrum than helium. So this is a great example of how spectra are actually fingerprints. So if you're in a lab, if you're an educator or you're doing other laboratory work with a spectrometer, you may have a gas tube like this casting a spectrum, and there you can see some bright lines. And then over here we have the actual intensity graph that we'll look at in a few minutes. This is a device that educators, whether it's high school or college, often use to teach spectroscopy because it's live. In fact, we actually have a camera here that is part of a system that we sell. So in 1835, and you can see we're jumping around time-wise here a little bit, Auguste Comte said the stars are just too far away for us to ever really know much about him. It wasn't very long after that that we were doing an enormous amount of astronomical spectroscopy. Well, Comte had no way of knowing these paradigm shifts and the new discoveries that we were going to make. But he was, of course, wrong. I sometimes wonder, what are we wrong about today, which in 20 or 30 years we'll look back on and go, how quaint that we thought that. So how do we get these lines? Very quickly, we'll race through it so that you understand what we're seeing on the stars. The Bohr model has shells where electrons are jumping between shells, and when they jump, they absorb or they give off different colors. To me, even this is amazing, that something at such a small level creates something at the scale that our coarse, relatively, eyes are able to detect. And so those shells and those transitions vary from star type to star type and material to material. This is an image I really like. There's Einstein on the right. Now, when I talked to clubs in the past that had live meetings with, if there were teenagers there or younger kids, I would point out Einstein here. Look at his posture. He's laid way back, you know, he's like this. And I would point out to these kids, so the next time your parents bug you about your posture, you tell them, you remind them about this Einstein slide. But then for the parents, I would pass on the fact that all the parents need to do is say, look, after you win your first Nobel Prize, you can sit in any posture you want. It's up to you. But until then, you sit up straight. Because, you know, posture actually affects mental attitude, they say in some studies that have been done. Here's some examples of some spectrographs. Again, I'm not going to get into a lot of details. This is the one on the right that discovered the first exoplanet, and it's in southern France. This is the VLT, and the scale of this is really remarkable. When you look at the scale of humans down here, you get a sense for how large that device is. And this is the Hubble Spectrograph being repaired by the space shuttle. Now, my son says that is not a spectrograph. He says that is a refrigerator, and it's filled with beer. And that you know, on the space shuttle, in the off hours when the cameras were off, they were real party animals. You know, what can I say? I think it's a spectrograph. And here is one on an amateur device. Now, this is far more complicated than what most of us, including myself, use. What I like about this is, you can see here Dale, and I know Dale, he's got like a gas tube shoved in there in order to do some calibration. I've always wondered, because you know those tubes have little, you know, those little high voltage pins right on the end. You can see them there out here. So what does he use? Alligator clips with his high voltage? You know, if you get a shock, you ruin your night vision. You know, that shock is just going to ruin things. It's not red light, I assure you of that. So, but what I wanted to talk about tonight was the star analyzer grading. And this is what most people, most amateurs start with, because it's inexpensive and really easy and a great learning tool. It's just 1.25 inch grating that screws onto almost any camera nose piece. And you can see like that, it goes in filter wheels. There's lots of places it can be mounted. So most of the examples I'm going to show you tonight are from a Star Analyzer 100. If they aren't, I'll try and remember to point them out. I don't want to oversell what you can do with it. This is a great image right out of the gate. You can see there's the Star Analyzer on DSLR. Notice there's no tracking. This is pretty remarkable. With such small aperture and no tracking, you can actually get a spectrum. And there's the spectrum, and you can see some of the lines. These are the hydrogen bomber lines, which I meant to mention earlier, we're going to be seeing a lot of. But this is a little difficult to do. The aperture is small. You've got to set it up so things drift right. So this is typically how most of us use a Star Analyzer. If you've got even just a DSLR, hopefully tracking DSLR on some sort of mount, then you can just mount it on the, as an objective grating it's called, on the lens cap threads. And we have an adapter that lets you do that kind of thing. Or, you know, most any cooled fits camera, it doesn't have to be color, doesn't have to be black and white, can be mounted inside a filter wheel. And I showed you a moment ago an example of that being used with just that's a ZWO camera, as it turns out. Can be video, can be mono. Now, that device I just showed you is about $200. Now, if you step up, then you get a Slit, and that lets you do higher resolution, look at extended objects like the moon and like the gas giants. But again, you've got to be able to guide on this 20-micron slit and find objects and understand what you're doing. So I only know 1 or 2 people who have ever started out at this level. It's a big step to take. You can also piggyback on your current telescope so that while you're doing some high-end spectroscopy or some other imaging of any sort, visual imaging, you're doing spectra too. So there's lots of ways to go about this. Okay, now all that stuff's behind us. What can we actually do? And for this, I'm going to show you some examples. I wanted to make a little change here because we're going to get into the color realm of my presentation. This is, I think that's the bomber line that goes right through there. So how do we actually capture spectra? Well, we have the star, we put the grating in the light path, and we get, just like it's a prism, we get a rainbow. So what can we do? So here's the first slide of the kinds of things that you can do. This is qualitative. So each of these is a different spectrum captured at a different time of different stars, starting with hot type B stars and going down to cool type M stars. Notice the differences. This is what astrophysics has developed. I mean, I'm a little awkward in that sentence just then because I'm so stunned, and I'm not pretending here. I'm so stunned at this pinnacle of knowledge that humanity over the last couple of centuries has climbed. Imagine, I mean, it's just stunning to me. So look at those differences for a second. You'll see here, for example, that absorption line is really much stronger then the same absorption line there, and in fact, that absorption line doesn't even exist down there on these cool type K and M stars. That's a hydrogen beta line, by the way. What about these, oh, gee, I didn't know how to do that. So what about these bands here? Well, on these cool type M stars, they're cool enough that their atmosphere contains some molecules. How do I know that? Because when I started reading about bands, I thought, well, what are these bands about? And Wikipedia is your friend. And I actually remembered it because it was my data. So this is done, by the way, you can see up here at the top with just a small Newtonian and a video camera by Torsten Hansen. This is really pretty amazing. The cool thing about video is it's live, so you get live focusing and exposure setting and all of that, but you don't need to use video. So now if we want to do quantitative data, then now first of all, that crosshair I just put up there, I'm betting most of you can't see that there's a little bit of dimming there. Maybe you can. But you know, science isn't done by saying, yeah, I studied the star and there was a little bit of dimming about a third of the way in the robin egg blue. We need to get quantitative. And that's what we do with this graph. This is simply an intensity graph of that image we captured there. So this star is very bright, so we get a very bright peak. And this broad peak is that broad data through there. And that dip there is the absorption line from up top. Now we're doing science. Now we can say we had an absorption line, it was this far away from the star, and so forth. Okay, let me clear that. Oh, okay, we got one more visual aid there on my slides. So this is the software that you saw a screen of a moment ago. And I'm going to spend 2 minutes. Julian, you time me, but wait, let me get started here. I'm going to come out of this screen and go into the software. Let's see if I can pull it off in 2 minutes. So you can see my, Julian, you can see my software screen here, right? Shake your head, yeah. Good, thank you. Thumbs up works too. So this is an image. It could be a live video. It could be a FITS image that you had loaded automatically as it hit your hard disk. There's the star, there's the spectrum. We bracket it in with this sampling line. And over here, let me get that out of the way. Over here, we have the same intensity graph we were looking at a moment ago. That peak there is from the star, and this data there is from that. And you can even probably see on your monitor a little dip there that shows up there. So we're now doing science with a $200 grading and the software, which is $100. So now I'm going to show one other thing here, and that is, you see those dips there? How do we know what those dips are? Well, we can pop up this little internal library in the software and say, show me where the Balmer series is, where the absorption lines for hydrogen would be. And when we turn those lines on, we get a template overlay, and we can see there, that's the hydrogen Balmer series. There's hydrogen alpha, hydrogen beta, hydrogen gamma. So that's all I want to show you about the software, because I want you to see how easy it is to do this. You can literally show this live on the sidewalk. Remember this image here with these hydrogen lines through it, because we're going to come back to that in a little bit. So let me minimize that and get back to the slideshow if I can. Great. So let's look at some other examples. Here's a wide field view done with a DSLR. And you can see there's differences here. Notice down here are some emission lines. Up here is an absorption line with an emission line or an absorption line. So again, just to give you a sense for the fact that this isn't some magic that you have to do a lot of processing to get. This is what you see when you look through your camera. So Janet Simpson out of the UK sent me this spectrum of a Wolf-Rayet A star some years ago. And this was done with just a DSLR and some mechanical tracking. Now, when we throw the software, we'll come back to what I was just about to say. When we throw that spectrum into the software, we see some very strong peaks. And again, you can see they're labeled here. These are carbon. We've got some helium emission lines, these bright lines down here. So then this is my confession to all of you. When she sent this to me, I couldn't remember what a Wolf-Rayet star was. All right, so we don't see Wolf-Rayet stars very often. So Wikipedia, again, is your friend. You know, Wolf-Rayet stars are late-stage stars where a lot of the outer atmosphere has been blown away, and we're looking down into some of the byproducts of the star's life. We're seeing some of the carbon glowing towards the core of that star. And the reason these are such wide lines is because there's an intense stellar wind on this star. So that's the kind of thing that you can image with pretty simple equipment. So now I want to show you the problem with extended objects. There's our beloved M57, and you can see it's an extended object. This is probably the only object that's interesting with a slitless grating like the Star Analyzer, because again, there's only really two different wavelengths that this thing is emitting: ionized oxygen and some hydrogen. So I mean, it's a marginal interest. But here's M42, again, hydrogen alpha, ionized oxygen, but this is done with a slit. And so that's why these lines are so narrow. But I wanted to just stop my banter for a while and pause with the slideshow and ask you to think back to the first time that you looked through a telescope and saw M42. Or maybe M42 wasn't the first time. But for me, it was at a star party in Denver. And it's fun to think back, and you should about your experience too. I saw all these things that looked like those cannons that they shoot people out of in the circus. You know, they were daubs, but I didn't know any better. And everybody's all excited, and I can't wait to get up to the telescope. And I look through at M42, and it's a smudge. It's nothing. I'm not dissembling here. I was really let down. But I keep coming back to look at M42 today, and you probably do too. Why? If it's such a boring smudge, why are we still looking at it? Well, I would say that the reason we're looking at it is because now we come to the telescope with some understanding about what we're looking at. It's a stellar nursery, it's a birthplace of stars, and that knowledge enhances our experience. And that's what the Star Analyzer and spectroscopy have done for me. Okay, we're going to move fast here. I just want to show you some other examples of cool things that we can do. Here's Uranus in mono. This is also done by Torsten Hansen, so this was also a video. You can see some absorption lines there. And when we say line, we simply mean a gap. And there they are showing up in the software. And we're actually detecting the methane on Uranus and Neptune. So again, this is mind-blowing. I know professionals, say 40 or 50 years ago, would have given their left arm, right, to be able to do this thing. And now on a backyard telescope, it's really incredible. So here's our beloved Albireo that we heard about a little earlier. And you can see that Albireo B happens to be blue, so more of the temperature and energy is down here in the blue end of the spectrum. And Albireo A is over here with more energy to the right in the cooler yellow-red. I'd sort of hoped that this would have been more pronounced, but nature didn't contribute or cooperate. So Henry Draper in 1881 imaged a comet. There's a comet image done by Vikrant Agnihotri. He's out of India. He's a nuclear power plant engineer in Rajasthan. And you can see the swan bands there. Again, comets are extended objects, so there can be a challenge to get a spectrum from them. But if they're compact enough in the core, then you can use a slitless grating. This one I really love. And the reason I love it is anybody who uses a C-clamp on their telescope setup is my kind of observer. There's a Star Analyzer on a video camera, and there's a meteor spectrum down there. Again, there's some people who are doing this. It's not as easy as things that are always visible. It takes a little bit of work. And the comet is, or excuse me, the meteor is moving in that direction. And at this moment, there was a bolide, and you can see some brightening. And again, here's the spectrum and some of the tentatively identified lines on that spectrum. It's pretty cool. It's a sort of a sub-branch of what a lot of us do. And it does take a little more work, as I said. So flash spectrum, again, most of you know the story of our discovery of helium on the sun. I'm not going to get into that right now, except to point out that this is a spectrum that you can capture on your own. And with really simple gear. It's pretty fun to do. So let's look at some novae. I know that we've got some novae hunters here. And again, you can see the different components. Different novae have different spectra. And again, you can see, what did I want to circle down there? Oh, that it's a Canon DSLR. So quick review for those of you who already know this. Doppler shift. Everybody's wondering, how good a job is he going to do explaining it? It's not going to be good, I assure you. Doppler shift is the change in pitch that you hear when a train goes through a station, right? Coming toward you, going away. Same thing happens with light. And so if something is going away from you, the lines shift either to the right, or if it's going coming towards you, blue. So here is a supernova there. There's an example of this type of supernova, but not this particular supernova. There's its spectrum, and there is the profile graph. Notice over on the right that David Strange did this with a 9-inch telescope in less than 15 minutes of integration time. So if we continue on here, you can see that there's a gap in the spectrum that produces that deep dip. And that deep dip is at about 6150 angstroms. So I'm going to jump through a couple of bullets here. Hang on there if this isn't your cup of tea. So below, David measured, as I said, 6150 for that wavelength. So if Bunsen was to have burnt silicon at rest, he would have found it at a different wavelength. So we know that something has shifted that light. And again, it's cosmological shift. Now, I honestly couldn't remember the Doppler shift formula. Again, Wikipedia is your friend. You plug the numbers above into that, and you determine that the shell of that supernova, this isn't cosmological shift, we'll get to that in a minute. The shell of that supernova is coming towards you really fast and shifting the light into blue. There should be two wows there. One is, wow, that's fast, and the second is, wow, I can't believe I was able to do that with such a simple piece of equipment. Now, Adam Rees, just to remind you, in the Nobel Prize he got a few years ago, now 9 years ago, for work that he did just before the turn of the century, used supernovae as his standard candles. Type 1a supernovae like this. So for me, it's really exciting to be able to do this kind of thing. Here is a series of spectra done over time, and you can see that that dip there starts out very blue shifted here at day 1, but over time flattens out as the shell becomes more and more diffuse. We're now able to see more of the original light from the star rather than that expanding shell. And I can't remember oh, let's see if it says on the side there. It doesn't say what equipment they use, but this wasn't some mountaintop. Okay, now here's fun. There is 3C273, captured by David Hayworth out of Portland. Now, truth be known, I've never seen 3C273, never imaged it, would never be able to find it. But you can do a lot not knowing very much. I'm proof of that. So there's the spectrum. There it is there. Hey, you know, I just glanced over at Julian there. Sorry to capture your attention. Did I do it under 2 minutes, Julian? Or did it take a little longer than that? With that software demo, was it a little longer than 2 minutes? Oh, okay, good. Thank goodness. I'd never done that challenge before. I'm glad I pulled it off. So, okay. So there's the spectrum. There's the two peaks. There they are graphed out. There's actually more than two. Notice that we can't even see them visually here, but when you graph them, they become very clear. Now, in the mid-1960s, this guy who, I hate to keep calling you out, Julian. I'm really sorry. You should have joined the meeting later so that visually I didn't see you on the list of 6 people who I'm seeing. But this guy wasn't much older than you. He was in his mid-20s. And he was looking at this spectrum. He couldn't figure out what it was. There's a wonderful transcript of an interview with him where he describes his discovery of what this was. And he wasn't sure he was right. He was worried that if he published it, you know, he'd be laughed out of the academy because he had missed some simple explanation. But what he did was he almost stumbled across it, but he was being thorough. He was a scientist. He took the spectrum of hydrogen from Vega, and you saw the spectrum in my software. I suggested you remember that display. And he compared the hydrogen bomber lines there to the hydrogen bomber lines in the quasar. And he said, wow, they're spaced right, but they're shifted. And the only way they could have been shifted is if this was really a distant, distant object, about 2 billion light years away. And in order to be visible from that distance, it had to be incredibly bright. And that was the discovery, that there were enormously bright objects that existed that we could see. They had to be enormously bright. So he was able to calculate whether it's him or amateur today. And this again is about 15 minutes of integration on an 8-inch telescope at a relatively dark sky site. The velocity of that light, but the redshift, let's call it, from the cosmological shift of the universe expanding. That's pretty amazing. For me, what's amazing is that light has been traveling for 2 billion years, let's say, and it still has information in it that we can tease out in our backyards. Unfortunately, humans don't age quite as well. There's Martin Schmidt today. And again, I took my wig off because I didn't want you to think that I was throwing stones without recognizing I was living in a glass house. So far, everything we've looked at, and we're going to finish up in the next few minutes. So far, everything we've looked at have been, features like these hydrogen beta lines, hydrogen bomber lines in Vega. And the resolution of that is about 50 angstroms, right? We're just looking at things about that wide. If we want to drill down and really look at that detail, that's when we need to step up to a slit device. And there's two things I forgot. This is a great talk. I may not be able to find it to show you. Give me a second here. Don't go away. Well, I can't find the one thing, but while I'm up, I'm going to get something else. And this is just a magazine. I don't need to advertise. So what I wanted to show you, and we'll look at it on the next slide, but on this slide with a slit device, you can see the spectrum of two different objects, Vega and the moon. Now, the moon isn't really appreciably moving towards or away from us, so there's no radial velocity or red or blue shift, but Vega is, and that's the difference. But again, look at the resolution we need down there. We need considerably higher resolution than what we're getting with the Star Analyzer, and that's when you step up to $2,000, $3,000, $4,000 devices. Okay, so I wanted to show you this slide, and what I wanted to show you was the absorption line of two different stars. It's really bugging me. I couldn't find what I was looking for, but I'll just have to use some other visual aid. Okay, so pretend this is a planet and it's rotating. So this edge is coming towards you, right? So there's blue shift on that edge. I had to remember. And on this edge, there's red shift, right? Because it's coming towards, well, it's coming towards you here and away from you here. Depends on whether it's me or you's perspective. Me or you's, what kind of English is that? So when that happens, you get red and blue shift. So if a planet is spinning very fast, you get this flattening here. And that flattening is Altair, which is spinning much faster than Vega, which has a nice sharp dip. So that's one way that we study the rotational speed of stars. Okay, how do you get started? Let's race through these and be done with it. Diffraction grating, I mentioned. Let's go back. I don't want you looking at all those words while I'm talking. So, I didn't want to show you that, but what I wanted to show you, and actually, I really didn't. Dovid is laughing at me. No, I'm just a klutz. I'm not like doing stealth marketing here. I should ask one of you to pull the Sky and Telescope off your shelf, but that takes too long. So here's an image just in the back. You know, this is an amateur image. And this is credit where credit's due. Terry Hancock, oh, it happens to be Orion that I was just complaining about. Total exposure time is 6.7 hours over 5 nights. And like I said in that bulleted list early on, numbered list, I don't have the skill, the dark sky, the equipment, or the interest in losing that much sleep or doing things overnight. I'm glad people like that do it. But because the results are these amazing images. But The reason I bring that up is because I want you to appreciate, I know I'm almost beating a dead horse at this point, and for a vegetarian, that's quite a thing. That what I'm showing you, you could be doing. Jane has done some of it. Other people, Julian has done some of it. Other people have done things who are here in the meeting. You can do this kind of thing. I'll tell you, just to throw these magazines under the bus for a second, I think when we all got started and we were looking at images like that, we went, oh, I want to get me some of that. I'll get a telescope and a camera. I don't even, you know, in fact, I sort of blew the story. You don't even need a camera. When you first see those, you go, oh, I'll just look through my eyepiece. And then we realized it's not so easy. There's a little bit of, I wouldn't say deliberate deception, but we're a little misled by those beautiful photographs until we get ourselves a little better informed. And I want you to understand that what all the stuff I'm showing you, with the exception of the slit spectra, which this is one of two, is something you can do with really simple gear. Okay, enough of that. Diffraction grading you need, a couple $100. You need some sort of camera, as I mentioned. Doesn't have to be color, doesn't have to be video, doesn't have to be a Fitz imaging camera. You might need a spacer, you might need some software. There's some freeware out there that I tried early on and decided to write my own. So resources, there's tons of books out there, and our site has a, what does R actually mean when I say our site? You know, it means me and my wife. We're not a big company. So there's lots of resources on my site and my wife's. And those resources include some really powerful tutorial videos that are really helpful. I think you'll be really surprised at how effective they are as a learning tool. The AVSO is now doing, they have their own Spectra database. There's a couple in the UK, there's one in France. So there's lots of interest in spectroscopy in the amateur world now. If you want to do pro-am work, there's opportunities to do that. Kristen Bwill's name you may recognize. He was a pioneer of CCD imaging for us all in the 90s. There's a variety of others, many out of France. Olivier is the one of the people who created the L-high-res slit spectrometer, and Bob Stenzel's out of the University of Colorado. So there are things you can do, but not that many right now. There are databases you can contribute to, and for me, it's a lot more exciting than photometry, which is why I mentioned it. So we've come a long way in the last 200 or 300 years. We've come a long way in the last 40 minutes. I know it's like drinking from a fire hose, and for that I apologize. Whether it's Fraunhofer on the left here or Kirchhoff on the right, as I mentioned earlier, and you've heard it in the past, we are standing on the shoulders of giants, and it's an exciting view, and we have a responsibility to pass this knowledge on, whether it's how to do these things specifically or just the general understanding that we can share with the public. Hopefully we'll be able to go out and do more sidewalk astronomy in the near future. And I'd like to thank all of you for, as I mentioned earlier, for the outreach and educational work that you do. And also thank you for coming tonight and bearing with my stupid jokes and ad-libbing. I appreciate the opportunity to talk to you. I hope to get lots of questions and you can prove or confirm how little I know about the science and telescopes. I'm really just a knuckle-dragging programmer. So that's my talk for tonight. Thank you so much.
Thank you so much, Tom. That was fantastic. I have questions, but before I get to any of mine, there's actually a few that have already popped up on the chat. First off, Danny wants you to know that you're not a wannabe. You're definitely cool. I think we all concur on that. Max has a question. I'm actually going to ask Max if he wants to unmute and ask himself. Otherwise, I'll go ahead. He's asking how unmodified cameras affect the results, and do you correct for them?
Really good question, Max. And if you'll forgive me, I am going to share my screen again, if I can remember how to do that. Can you set me up to share my screen?
Yeah.
Oh, there we go. I'm ready to go.
Yep.
Yeah, good. Because basically what Max is saying is, this doesn't look like a Planck curve to me, right, Max? So, and the reason why not is because our cameras lose sensitivity out in the blue and out in the red, right? They're just, you know, they've got a response curve, the quantum efficiency of our cameras. And in fact, just to confirm that, I want to show you something pretty cool. Here's a reference library of corrected curves. These are ones that they've eliminated the effects of the camera. Let's bring up a type A star. I thought I was going to bring up a type A star. There we go. That's the curve Max was expecting, right? Because then we can look where the peak is, we can calculate the temperature, all those things. Why does our curve go down? Well, as I said, because our cameras lose sensitivity. There's most of the time, as amateurs, we're actually looking for features. And the features are still visible. In fact, look at this. You can see there's the hydrogen beta on this professional spectrum, and there it is in red. There's ours, there's a professional. It's cool that they line up. It's pretty exciting when that happens. And same thing happens here. So there's a simple procedure that allows you to use this curve to calibrate your camera so that you get true curves here that reflect the temperature of the star. And in order to do that, there's a video on the site that explains it. The cool thing is if you do that across different stars, in fact, one last thing that is fun. Again, you're not going to be able to shut me up. You know, as soon as people start nodding off, and I'm watching now, I'm watching all of you, I'll shut up. I want to go through these stars here. This is pretty amazing. I don't know whether Julian and your colleagues there, your co-students did this or saw this in the video. So I'm just going to point out first, O star's hot, B, what, O be a fine, G, K, and then M. So now let's look at the type O stars. And notice a lot of its heat, most of its energy is over here in very high energy region, not in the visible region. And now instead of just stepping through one at a time like this, I'm going to hold down this button and it's going to go through these. Watch how this curve, as we go through the stars in Obeah-Fine Kiss Me order, migrates to the right. Watch that curve on the right, that blue curve. There it is, a little more to the right, a little more to the right. It's moving more. We're into the G stars, the K stars, and the M stars. Look how these cool M stars have so much of their energy over here in the red region and even in the infrared. Not that much in the visible range, and it doesn't look like there's any over here. So, Max, that's an excellent question. It's just to sum it up, this is as a result as you anticipated because our camera's not linear and it affects the colors, and there's a way to correct for that. I hope that answered your question, Max.
So Jane asked a question, and Jane, you know, and she's asking a question that actually I keep, every time I use RSpec, I'm asking myself this question the entire time. Is this the right dip for me to be setting as hydrogen alpha, hydrogen beta? How do I know I haven't caught noise? How do I know it's not my camera? How do I know it's not just something randomly affecting that?
That's a good question. Spectra? That's a really good question. First of all, I didn't know any dips when I started this, and I'm looking for a particular book. God, what an awful presentation. I don't have any of my aids in hand. I wanted to show it to you, though, if I could. And I can't. But there's lots of books linked to on our site that help you understand what you're seeing. But once we've calibrated this, and there's a step I didn't show you, but once we've calibrated it, which is a click or two, and we have these dips, what Jane's asking is, well, how do I know that's hydrogen beta? And how do I know that's hydrogen gamma or delta? Well, and that's where I picked up this, if I can find it, it's on another screen, there it is, this reference chart here. Now, all this is a list of the wavelengths that Bunsen discovered when he burnt hydrogen. And when we asked the software to display them, those lines are superimposed on our graph. And really, it's a numbers game. It's a matter of, well, let's see, those all seem to match up. I mean, there's a little bit of error here. I didn't do that good a job of calibrating it. But if they tend to align, if they tend to match, that's good evidence that you're observing and calibrating on the type of star that you think you are. This is a type A star. That particular type star has very strong hydrogen bomber lines. It's just the right temperature. It's not too hot, it's not too cold. So that's how you confirm that you're doing things right. Now, the other thing you can do, as I showed earlier, is you can open up the reference library and just display the curves from the reference library. And when you see those curves, you see that they also correspond. Let me just make one minor adjustment here. Let's do that. And go to that again. There we go. And now what I want to do is that button and just adjust the relative height so you can see the match. Look how those match. Professional data, our data. Our data, professional data. Our data, professional data. There's really a match. Now, what are all these? Now, they're books, they're reference books, and it's still bugging me that I can't find that book. There are reference books that can help you understand what those things are. And also the forum. You can post stuff and say, does anybody know what this is? That kind of thing. So the devil's in the details. And the good news is that you can't see tons and tons of lines with a low resolution grading. So there aren't going to be a lot of things you can identify because there just aren't a lot of things. So I hope that's some help to you, Jane, and others. So other questions?
Based on that, one of the things that we've been doing is we've been starting with Vega for any new user to start with a very easy to spot, nice and bright star. Yeah. But Max asked an interesting question because we know that we can get some level of relative luminosity, like when we have double stars like Alvario and we compare the total intensity spectrum. But what about the size of the dips? What can we gain in terms of information from the intensity of those? Max was asking that.
Good question. Really good question. In fact, professionals don't use the shape of this curve to measure the temperature of a star. I mean, originally they did, but now, I'm just editing some things I don't want to say, just in terms of the history of what I'm about to say. Now they use the presence of different lines. Not only whether the line is there, but how strong the line is, how wide the line is. And they actually look at the ratio of the line width between helium and some other elements. And that measures something about the metallicity of the star. And then they can understand from that at what stage on the HR diagram, this is all for you guys, the HR diagram, is that right? No, it would be that way. The HR diagram is. So the way you measure the width of one of these things, because every camera has different sensitivity, right? The way you measure the width, just to show you another interesting thing about the graphics here, is if you drag these lines around a feature like that, more or less symmetrically, down here, the software is going to show you what the full width half maximum of that line is. There it is. There it is geometrically that you can see. So again, full width half maximum means the maximum is this distance, right? And half that distance is here, and that's the width. So half width. And so by taking that number and comparing it to the full width half maximum of other elements, you can tell something about the composition of the star. That's rather advanced to do, and amateurs do some of that, typically with slit spectra, just because the slit eliminates a lot of the background noise from the sky, and they're more likely to get good results. But while I'm talking about things you can see, one thing you can't see that all of us want to see is the radial velocity of any object in our galaxy. They're just not moving fast enough. You know, our resolution is too low on a device like this. Even the multi-$1,000 devices, it's very difficult to have the kind of repeatable resolution you need to detect radial velocity, because I think all of us want to discover the next exoplanet using spectroscopic radial velocity. It's tough to do. So that's my answer.
But now with that, would we be able to do real-time luminosity curves to see an exoplanet transit? So can we use that for variable stars or exoplanet transits or something like that?
Even exoplanet transits are tough to do, as you know. And what you don't want to do where you've got, you know, very small tolerance of error on exoplanet light curves is you don't want to take, normally when we image a star, all the photons are what, on a handful of pixels.
Yeah.
But when we spread the light out across hundreds of pixels, we lose 5 or 6 magnitudes. And so, again, that's just going to really mess with our signal to noise ratio when we're trying to detect exoplanets. So we don't gain anything for when we're looking at light curves by using a spectrum. The best thing is just to use a star and use the established procedures for that. It's a really good question, though.
If we look at something like Cepheid variables, would you be able to see the change in the helium lines over a few days?
Yes,
Okay.
you can. Give me a moment here, just to clean up the screen. I'm just thinking, you know, I guess there's nothing very damning on here. I'm not going to even bother hiding my my favorites. I should have prepared for this. You can see I'm doing some workouts here. And
No worries. None of us are looking.
no, I mean, there's really nothing damning on my computer ever. But the reason I wanted to show you that was I wanted to show you on our site under sample projects. And you should take a look at this, because this is, again, examples. If you don't want to wade through this whole video tomorrow when you're trying to remember what was said, a lot of them are on the site under the samples button. Notice the samples is the second link after home, only because I think this is the most important page. But what I wanted to show you, you were asking, I'm sorry if you need some Dramamine for this part of the presentation, is Cepheid. Well, hold on, L-R-Y.
There.
Oh, there it is. Was it there?
It was there, yeah.
There it is. Thank you. Jeez. Okay. I want to show you this animation. And we just have to click the image. I think it'll be fast enough. So this is over just 2 hours with just a 4-inch refractor. Look at the shape of that curve change. It gets hotter and hotter and harder. The bomber lines become more visible as it gets hotter. Can you see that? So you can study the changes in light curves. Now, this animation wasn't made in RSpec, but the data could be captured in RSpec. So this is done by a gentleman, Solicia, in Italy. Credit where credit's due, with a star analyzer and just a Tech 110. Is that the kind of thing you were asking about?
Exactly. Exactly.
Cool.
And
Great.
Max was asking if, when you talked about the dips and the relative intensities and doing the actual half width or maximum at half width,
yep.
You know what I'm talking about.
Yeah.
What about the gas clouds that the light passes through on its way to us? How much does that affect what you're seeing when it's a dispersed cloud or when it's our atmosphere or something along those lines?
That is also a great question. Max, thank you. It looks like I shut down my software, so let me start. Oh, there it is. Okay. Under help in our system is a section or a PDF determining a star's temperature. And I'm just going to go to that and refer to it real briefly. If I can bring it up here. Well, give me a second to get it onto the right screen. Here is how we tell star types. In other words, stars, and we saw this earlier, type A stars have the most hydrogen. This is just a relative strength of different elements lines. Here, these cool stars have lots of this molecule, titanium oxide. Really hot stars have a lot of ionized helium. So, but the reason astronomers don't use the spectral energy distribution, that sort of general color curve, and instead use the presence of elements, is for just what you asked, Max. That's a great question, because Wien's law doesn't work accurately to determine star temperature. I know it's heretical to say, but the reason it doesn't work is, for one, the very question you asked, Max. Between the star and us can be a lot of interstellar gas that can redden that image. So we can't really use the spectral energy distribution. The other problem is that here's Vega. And this is the Vega curve that we would get if we corrected. But this is the Planck curve for a star of that temperature, because there's a lot of energy down here that's outside the visual range that has to be taken into account when we're doing Wien's law. So determining temperature by the shape of the curve is not the right approach. And indeed, Max, even when you're doing the full width half maximum relative ratios of different elements, the intervening materials have to be taken into account. Some of the reference libraries that professionals publish will have two. One's called the Miles data reference. Have two stars. One which has a reddened image that is a star that came through some interstellar gas, and another which is a star that, to the best of our knowledge, doesn't have that reddening from interstellar gas. So a lot of the determination of that depends on our stellar models. We're pretty good at predicting what the curve of a star should be from the models that we have, which is really one of the indicators that our models are right, is they match real life. What else?
So you've gotten me into a lot of trouble with all my former students by saying that Wien's law wasn't the right one to use.
Well,
So.
I don't push me on that. But there is some.
You're right. You're right.
Yeah. But it's a really helpful. It doesn't mean Wien's law is worthless. It's still really important that your students learn that temperature is related to where on the energy angstroms curve the energy is coming from.
It's all about how the starlight gets to us, and that's part of the key. And one of the things that I really love that you showed is the fact that the fast rotating Altair flattens out those dips, and that's something that's just fantastic to be able to see just with a simple setup like the Star Analyzer.
Yeah, well, again, the Star Analyzer may have trouble seeing much of that. The prop I was looking for that I wasn't able to find is actually a soccer ball that I use as opposed to this flattened star, where I again show the rotation where you have some light coming towards you and other light moving away from you.
So I'm going to go ahead and stop the recording, but invite everyone to unmute their mics and go ahead and chat with Tom for a bit before I'm assuming that at some point he'll have to go because we're probably starting to bite into his dinner time, etc. But
hey, I would fast to have this opportunity. I love talking to you folks. So
fantastic. Then I'll invite everyone to unmute and we'll stop sharing the screen and we'll just start into like a general discussion. Thank you again on behalf of RASC Montreal Center, John Abbott College, and all of RASC. We were really appreciative. And
my pleasure.
Lots of claps happening, lots of thumbs up and thank yous in the chat.
Oh, good. Glad to hear it.